Okay. All right. So I'm gonna go ahead and get us started. So again, thank you for joining us this morning for our second roundtable of the series. This is presented by PCE and SVCE, and is a clean energy, Silicon Valley Clean Energy. So the topic for today is high-rise multifamily domestic hot water. Um, on the screen that you're seeing right now, I also have a summary of our previous event, which was on low-rise residential, and also a summary of what are some roundtables that you can expect to see for the next couple years. So, to the next slide. So my name is Myra Vega, and I will go through who our presenters are for today. And I am with TRC. We were contracted by PC and SVCE to put this presentation and this series on for all of you. A little bit of using GoToMeeting, which is the format that we're using. You will notice your control panel in the corner. It's usually on the upper right corner of your screen. Um, we do ask that you remain muted. Through the presentation, as you want to ask questions, I will unmute you, and then you will have to unmute yourself after that if you want to ask a question. Um, we do ask that you engage with us. This is when we first developed this. It was pre-COVID, and so we really wanted these to be in-person, interactive roundtable events. And now that we've moved on to a virtual event, we're having to be a little bit more creative. So we really encourage you to type your questions into the chat box. We will be monitoring those questions throughout the presentation and give you an opportunity to ask those. Next slide. So for today, this is our agenda. I'll be doing a brief introduction, and then we have Eric Soto with DNS Development. They have an all-electric high-rise multifamily building in Sacramento. He'll be talking about his experience with all-electric design. And then we'll be moving on to the designer perspective of Sean Oram with Ecotope. He'll be walking through kind of his experience and his process with domestic hot water systems in multifamily, high-rise multifamily buildings. Then we'll move on to the Q&A. So this is an opportunity where you'll be able to ask questions. We also have a couple projects that have graciously volunteered to talk about the struggles that they're going through their projects as it relates to all electric design. So we'll have an opportunity to talk about those. Then we'll move on to brief topics. So these are all electric technologies for high-rise multifamily buildings. And then we will close out the presentation. All right, so for today, these are your co-organizers and presenters, myself, Myra Vega with TRC. We have Blake Kershaft with DNV. Again, presenting the developer's perspective on all electric design is Eric Soto. And then giving the designer's perspective is Sean Oram. All right, so just a brief, before we get into Eric's presentation, just a brief overview of why we're doing this. As you all may be aware, there's been quite a bit of movement in passing some state legislation on reducing our carbon footprint. A lot of that has also been targeted to buildings, and we also acknowledge that that can present financial and technical difficulties for the development teams. And so we are providing this series to help developers and designers make those decisions that work for the developers' pockets and also for the tenants and for whoever is actually living in the buildings. Alongside of state legislation, we also have various cities throughout the state that are adopting REACH codes. And so they range from all electric preferred to all electric required to having an actual natural gas ban. And so because these are going to be, we're going to see these reach codes, uh, they're just going to, more cities are just going to keep on adopting these types of reach codes. And so we want to make sure that you are prepared and want to provide this resource while it's available to help you make types of decisions you need to design your all electric buildings. And this is just to give, this is just to kind of frame the presentation. There's a variety of perceived barriers to all electric construction, and so we definitely want to, we're aware of those and we want to address those. And with that, I'll kick it over to Eric. Yeah.
Yeah. Thanks, Mara. Did you give me control? There you go.
Yeah, hold on.
All right, Mara, let me know if you can see my screen and which screen you can actually see.
We can see the screen with your presentation and the notes.
Oh, and the notes. Okay. All right. Are you able to see the presentation now? Sorry, I got 3 screens I'm working with.
Now we can see your desktop.
Mara?
Yes.
Okay, you can see my screen then.
Yes, now we can see your screen.
All right. Hi, everyone.
All right,
Sorry
take
for
it away.
that. I was working with 3 screens. Had to just move it to the simple laptop and keep it simple. So my name is Eric Soto. I'm a project manager at DNS Development. We're a development firm in Sacramento, kind of focused on the Sacramento region. And our bread and butter tends to be these urban infill, mixed-use type products. So I was going to briefly introduce 17 Central, which is currently under construction, which is also an all-electric building, and we are utilizing the heat pump water heater system. So quick project overview. The project is an urban infill new construction in the downtown Sacramento area. It's 8 stories tall, about 94,000 square feet total, and it's a very small footprint, 80 by 160. So it's a tight lot, it's 0 lot line building. So it's very tight, typical in urban infill. It's a mixed use product, retail on the first floor and market rate above, market rate apartments above. Total of 111 units, a mix of studios and 1 bedroom, 1 bath. So we decided to go all electric, maybe around 50% DDs, for many reasons. One being macroeconomics and kind of macro trends towards decarbonization, um, and uh, and kind of the trend of the penetration of renewable energy and anticipating lower electricity costs. We also wanted to address climate change as developers, as responsible developers. And third, as much as we love working with utilities, I think it was nice to work with, it is nice to work with one utility, with a Sacramento Municipal Utility District, or also known as SMUD, who is the electrical provider in the Sacramento region. We were also working with them to underground their overhead lines. So it was kind of this synergy approach where we were already familiar with the operations and the team. And lastly was, and most importantly, the incentives that SMUD offered for appliances and all electrification, or for the electrification of our project. So we did consider, when we initially designed the building, we were initially going gas boiler. which is the conventional approach, kind of what everyone does. It's cost effective. But this was kind of during the campfire, and we were just really uncertain of where gas prices were going to go. And in addition, we had to bring gas into the building again. And so we started exploring the all electric building. And so we initially designed, or we moved to a resistance water heater. So this was kind of nice because it was least cost. It's something everyone's familiar with. We used to have it in our homes, but this required a high amperage and put a lot of stress on our transformer design. And so after that, we kind of considered heat pump water heaters, but the 50 gallons that are kind of common in households, and we were just going to put 50-gallon heat pump water heaters and kind of split them between units. But this would reduce our leasable square footage, and we have additional compressors. We didn't know where to put them. It was, again, it's a small lot. So we eventually settled on the centralized heat pump water heater system. So like any development, there are several challenges. I'll kind of just touch on the more important ones, which are the darker shades. So one, this was our first attempt. So I myself participated in a lot of webinars about heat pump water heaters, very much like this one. Just kind of learn the process, learn what it's all about. And then I'll briefly talk about hard costs later on as well, and the funding. And then another issue was our transformer size. We were on the cusp of a 480 volt transformer. We have two transformers in our building, and the 480 volt was just too large and just too expensive, and so we had to really turn a lot of dials and a lot of knobs to drop down to a 208. And one of the last major issues is, will it work? No, this is our first time doing it. And so our plan B was actually to kind of design the building to handle a resistance water heater just in case. So we have a 1200 amp panel. And so our loads are kind of designed to handle a resistance water heater if we need to convert back. So the overall system, sorry, I'm gonna hide this. So the overall system that we used the Colmac CXV5 heat pumps. We had about 5 of them, and to heat the water, and then we would store it in the A.O. Smith storage tanks, about 350 gallons, so about 1,050 gallons total worth of storage. So the way it works is the city water at the bottom left corner of the screen comes in, goes into our heat pumps, which are lined up in parallel. The water's heated up to 40 degrees and kind of bifurcates into the storage tanks, which are set up in series, and into the mixing valve. The mixing valve cools down the water to 120 and out to the units. We also anticipated a 10-degree drop in the recirculation, which would eventually end up back into the system and kind of recycle all over again. So our boiler room was initially designed for a gas boiler. The size was we moved it a little bit, made it a little bit larger to take care of the heat pumps, but we located it on the first floor because we didn't have a basement and there was no room on the roof with how small the lot is. And so it's adjacent to 17th Street on the south side of your screen, or the bottom part of your screen. And if you blow this up, you can really see how tight the storage room is, or the boiler room is. We ended up having to stack our the left side of the storage room or the boiler room. You have two where the actually have two heat pumps stacked on top of each other with appropriate clearances, of course. And then the fifth heat pump is on the right side of the room above the backflow preventers and the booster pump. And then the 3 circles are the storage tanks in the back of the room. So to address right now is the overcooling of the boiler room. So what we did initially was we installed a louver system and an exhaust fan adjacent to the garage to kind of pull in the hot air from the garage into the room so that the pumps didn't overcool the room, and then any excess air would be expelled in that entrance door on the bottom part of the room through louvers. But after a long, very educational session with Sean, our taking a second look at the heat pump location, and I think trying to revisit the air exchange between the rooms, and we might actually reconsider moving our heat pumps out into the garage. So now it comes down to the actual cost of the systems. Um, so our proposals actually came out to 100 for the system itself, not including install or the plumbing or the labor, but the material itself came out to 113,000. We were luckily able to avoid the swing tank, which you can see in the top table. I just threw that up there so you guys have something to reference when you kind of do your cost analysis. On the table, you can compare that to the resistance tank that we initially quoted for about 38,000, and to the gas boiler, which is from a project of similar size, maybe a little bit larger, but it was about 80,000. So you see the cost difference between the resistance water heater and a heat pump water heater, and between a gas boiler and a heat pump water heater. And so what really drove the decision making were the incentives. SMUD had incentives for going all electric for all electric appliances. And so one of the main appliance where you kind of switch from gas to electric is really the range. And so you can kind of the quotes here on what a typical gas range would cost, what a typical electric, and an induction. So SMUD actually offered on the bottom table, you see the all electric incentives. SMUD offered 1250 a unit for all electric appliances, and if we were actually to upgrade to induction, we were able to get an additional 500. So you can see the total incentives came out to about $200,000 for going all electric on this building, which was probably one of the bigger drivers in the decision-making process. So now we're kind of comparing, we'll definitely try and go all electric, but we want to compare resistance with heat pump water heaters. And you can kind of see right now, the top right is the CXV5 heat pumps, and the bottom left is the resistance water heater spec. And you can see the power draw on these two units, 6.4 kilowatts versus 70 kilowatts. We have 5 heat pumps, so 32 kilowatts total. And if we were to use resistance water heaters, we'd have to use 3 of them, so about 216 kilowatts total. So it's pretty obvious that our electricity draw is going to be different, our demand is going to be different. We may potentially save money. So how does this really affect our OPEX or our operating expenditures or costs? And so the table up here you can see is our anticipated monthly expenditures for each of the 3 systems. And just to remind you of what the initial costs were, I'll throw that up there. So when we compare resistance water heaters versus heat pumps, it's pretty obvious we're saving about $4,000 a month on operating expenses. So right now, the resistance tank is about 75,000 cheaper. If you take that and divide it by the 4,000 that we're saving, we're actually able to recuperate our initial costs in a year and a half and kind of recover that additional $65,000 in costs switching from a resistance water heater to a heat pump water heater. So pretty obvious at that point, let's do heat pump water heater. But then we went back and we kind of tried to justify if it was even worth switching to a gas boiler from a heat pump water heater, because you can see from this table, it's obvious that gas is still cheaper in operating expenses. It's cheaper in initial costs and cheaper in operating. So right now the price is about gas, but that it kind of excludes our load shifts. We didn't really look into that on shifting loads to off-peak hours for lower pricing. But what it really came down to again was the incentives. If you take the gas boiler, it's about $33,000 cheaper, but we have a $200,000 incentive, so we're left with 167. If you take that 167 and you actually use that to pay off that additional dollar expenses, it'll cover 10 and a half years for the most part. And so if we kind of looked at it and we asked ourselves where do we see gas prices going in 10 years? where do we see electricity prices going in 10 years? And if you're particularly bullish on the penetration of renewable energy and kind of the either a stabilized or dropping rate in electricity prices, and you're especially bearish on where gas prices are going, then I think the heat pump water heater makes the most sense. And so with that, that's kind of the quick, brief look at our project and what we did at 17 Central. That helps you guys out in making decisions in the end. So I'm going to hand this off to Sean. Sean, did you get it?
Yeah, hold on a minute. Okay.
Hey, Sean, before you start, can everyone hear me?
Yeah.
Okay. So we are monitoring the chat box for questions, and so we will address those after Sean's presentation.
All right. All right. So I'm wondering, can you see the screen or not?
We can see.
Yes, it
We
looks
can
like
see your desk.
saving to a server.
Oh, yeah. All right.
No worries.
Okay. Big file. Close.
And before Sean starts, as he's saving his presentation, I'll also throw it out that, and you'll see it as we close out this presentation, that we are also offering technical assistance for project teams at no charge to you. And Sean Oram is actually one of our experts on that team. So if you sign up, you may be lucky to work with him more directly.
All right. Bear with me. Can you see this?
We can. You might want to expand it so we don't see your desktop behind it. And yeah,
Okay.
good to go.
Oh, great. All right. How's this look? Okay.
Perfect.
Sorry about that. Well, good morning, everyone. My name is Sean Oram with Ecotope. I'm Director of Design and Engineering. Ecotope's a small research and MEP firm up in Seattle, Washington. We've been working on central heat pump water heaters for about 10, 11 years. And so we are helping the region, so the West Coast region, kind of advance the whole cause around heat pump water heaters. So thanks for joining this presentation. So a little agenda, a little background on what I'm going to try to cover. I'm going to try to review some of the heat pump water heating kind of background material, as well as kind of run through some design considerations and then show you some project examples. So kind of at the high level, in Seattle climate, so this data is based off of Seattle. It's probably quite similar to Sacramento. It's a lot more rain. The multifamily domestic hot water end use is about 25% of our buildings up in the Northwest, and it's probably quite similar to buildings down in kind of the Sacramento area. I would say it's, there's going to be more space heating where we're at. So that could probably be replaced with more cooling because we don't have a lot of cooling load up in Seattle. Anyway, the takeaway here is that the domestic hot water load is about 15% of the total energy, and the temperature maintenance is about 10%. And so this is a very large load. It's been traditionally addressed through central gas boilers. So this presentation will kind of discuss replacing that load with high efficiency central heat pump water heaters. So a little, again, more background. Right now there's a a refrigerant phase out in play, and it's sort of in play. It's going to likely get a lot more strict in terms of what type of refrigerant and the GWP you're allowed. But it looks like the next sort of cutoff is going to be right around 700 GWP, which is global warming potential. And so a lot of the refrigerants that are being used now, I've sort of highlighted them. 134A down kind of in the middle has a GWP of 1430. That's a very common refrigerant for domestic hot water heating. 410A is not as common, mostly because it's limited on its high temperature output, but that is you know, the heat pump that Brian mentioned is actually a 410A device made by Colmac. Some of the other refrigerants that are coming to play, 744, which is at the top of the list, that's CO2. 290 is propane. That's another one. There are some products we're trying to bring to market that are propane based. There's also some synthetics, and then our 134A is likely going to be replaced by a new one, which is 513A. So there's a lot of numbers and letters in here, but just note that the transition is going to happen, and it's not clear exactly how California is going to treat this. So we'll see, but definitely keep an eye on that. I think what'll happen is most of the manufacturers will sort of do sort of swap outs of refrigerant with existing gear. So I think there's going to be a big market for that. Next piece is to cover kind of the central hot water heating systems, and really to identify and accept that there are two loads in any central hot water heating system. There's the primary water heating load and the temperature maintenance load. And if you look at the chart on the right, the primary water heating load is supplying the actual hot water that's being used in the apartments. And so this is really just making the cold water hot. We typically see between 16 and 22 gallons of domestic hot water per person per day. Really aggressive flow reduction and occupancy type will drive you to closer to the 16. And the higher numbers we see in market rate. 22 is about what we see up in Seattle. So those are two data points. We've got some others as well. And then the temperature maintenance is another load. And this is really just to keep the line primed. It is really hard to stop the loops or to stop the recirculation pumps in these systems. So you do have to be really careful. I know there are controls in Title 24 that require us to stop these loops when there's no demand. My argument is there's always demand in these buildings. Also, when the distances get beyond about 60 feet from your plant, you can't stop the loop, or else it's going to take forever to get your hot water. So this is a really crucial piece to the kind of the total system efficiency. So there's both the heat plant, but there's also the distribution system, and there's a lot of stuff happening right now around the distribution systems and how to really squeeze the losses out of them. So I showed you the two sort of loads, and the advice that I would give is you'll get the best results if you decouple the hot water circ loads from your primary heating. There's a lot of reasons for that. This doesn't mean it won't work, but I'm recommending that you decouple it in some way, shape, or form. I'll show you a graph in a minute on why, but I've shown sort of two schematics here. One is the swing tank schematic over to the left, and that's sort of a gang of heat pumps working on one sort of batch of storage. That storage is stratified, so we use single pass heat pumps, and we send the water to the top. And then there's a swing tank on the left, and that's used primarily to deal with the hot water circulation or the temperature maintenance load. So there's two ways to do that. You can do it with a swing tank. There's also a parallel loop tank. So when the loads get too big and essentially overwhelm your primary plant, then you want to consider a dedicated heat pump for your recirculation. And here's an example of why you want to do that. This is a performance chart for Nile and A.O. Smith heat pump. And if you look at the curve, you can see the bottom curve shows the air temperature. So that's the entering air entering the evaporator, which is where the part of the heat pump that sucks the heat out of the air. The heat capacity is shown on the left. And if you look at the 4 different curves, we've got 40, 60, entering water temp, 90, and 120. And you can see that if your return water temperature is really cold, you're going to get a lot of capacity. And that aligns well with, oh, oops, sorry about that. Let's see, how are things looking here? Looks like it popped me out. All right, so
You're good.
okay, good. So we've got, just to kind of follow through on this point, you can see the capacity difference. If the entering water is 40, you can see, we've got about 45,000 or 450,000 capacity. And if that same entering water with the same ambient condition and we've got 120 degree water coming into a 134A heat pump, we can see a really significant drop in output capacity. That difference in capacity at the same temperature is a direct hit to your COP. And so that difference in that capacity means that you've got to make that up with your compressor input energy. And so that you're going to take a really big hit. And so the takeaway here is that the reason to decouple the hot water primary hot water heating load from the temperature maintenance load is that you really want your heat pumps to see really cold water. The colder the water your heat pumps, the better, the higher capacity, the higher efficiency. So moving on to sort of the 2 different ways to do heat pump water heating at a central level. There's the single pass operation. Single pass is really heating your water up to the working temp in a single pass. Pretty straightforward. Typically, you're pulling from the bottom of a tank and you're dumping to the top of the tank. This is a really effective way to do load shift, and this is really what the region is sort of focused on. With single pass devices, especially CO2, we can make really hot water in a single pass, and that really helps to facilitate load shift. The other way is the multi-pass, and multi-pass is very similar to a gas boiler. We're heating the water up in sort of 10-degree slices. So every time it goes through the heat pump, we add another 10 degrees until we get to set point. These systems will require, if you run the recirc through that tank, which is very typical of multi-pass, your heat pumps will run all the time. And so we're trying to sort of set these up as thermal batteries. And this is the reason you want to sort of decouple the circ loads from the primary storage, is we want to have this reserve of really hot water so we can kind of float through the high peak rates. We've done heat pump designs with both single pass and multi-pass. And most of our single pass designs are more efficient than our multi-pass, and it's because of the entering water. Here's a kind of a bigger schematic, so it's very similar to what Brian showed. We've got a gang of heat pump. Or we've got our heat pump water heating plant over to the left. We've got our primary storage. We've got a swing tank. We've got our hot water circ return and our thermostatic mixing valve. And what we're showing here is the cold water comes in, it comes into this first tank. I like to use 3 tanks for primary storage, mostly because this isn't shown in the right place, but you can essentially get your thermal well sensing right in the middle tank. So this gives you enough time to drain this tank, and once it cools down to about the midpoint, then you fire it and you get a good long heat pump run. And so that's been a really popular, successful design for us in Seattle. And then the swing tank is over here to kind of deal with the hot water circ. The key point with single pass heat pump water heaters are to not let your heat pump see the hot water circ temperature. And so that's why decoupling this will preserve the efficiency of your single pass device for your primary storage. Remember, this is the majority of the load. Here's a
Hey,
swing
Sean.
tank. Yes.
quick question, going back a couple slides.
Okay.
For the single pass versus a multi-pass, I see the multi-pass is not as efficient because the single pass, is it a slightly more complicated design? And if so, is it more expensive to design? And do you
Yeah.
you
Yeah,
see
that's a
any trade-offs with the efficiency gains?
yeah, that's a good question. It really, the single pass really comes down to the kind of the equipment and the cycle. I don't think it's more expensive to do than a multi pass. It's more of a you know, we've the 134A machines out there, Nile, Colmac, and Mitsu and Senko too, can all do single pass. They some of those devices can also do multi pass. But I think that, you know, the costs really come out of, I mean, the heat pump costs, we've got the storage costs, and then the piping that connects it. So, you know, the piping, there might be a little more piping, but I don't think you'd see a whole lot of price difference between the two, other outside of kind of the specific heat pump technology, because we have seen a range in the cost of that. But I think you're going to get a lot more out of the single pass. The other part is that with single pass storage, the storage is actually more efficient. So you could, in theory, buy less storage with single pass. So I think that they're both probably, you know, they're both comparable, and I haven't seen a big price difference between the two, just based on whether it's single or multi. I think the variables that I've seen are mostly the equipment and how sophisticated it is.
Got it. Thank
Okay.
you. And one final question. Is there
Sure.
ever a scenario where you would recommend a multi-pass over a single pass?
That's a great question. You know, personally, we've done about 4 multi-pass designs, and I've seen them in play. So when we're doing multi-pass for the primary plant, um, you know, if one of the heat pumps goes out, you can potentially lose the entire system because your recirc is still flowing through your tanks, and so you strip out all that heat. Whereas when you decouple it, you still got that primary storage. But I think that yeah, yeah. Anyway, I lost my train of thought. Sorry. Let's see.
Yeah.
So I will continue here.
Yeah.
Sorry.
Thanks for
Um,
answering the question, Sean.
yeah. Um, let's see. So the swing tank with the single pass concept. This is some data we've got on one of our Elizabeth James. It's a project called Elizabeth James. It's a 60-unit low-income apartment, and we can see the flow data for 2 days. And this again is your primary storage feeding into the swing tank, and the bottom kind of shows the temperature of the swing tank. So during the low overnight use, you're bringing this hotter water that trickles through that final swing tank, and it'll essentially heat the recirculation load on its own. So it is a concept that works well. The next part, so that was a little bit of the background. The next part, I will get into kind of the central heat pump water heating design considerations. So this is again more background, but a little bit more specific. Here's kind of a summary of the basic approach, and then I'll kind of jump into it. But you know, utility impacts, there's plant sizing, there's equipment manufacturers, there's the plant location options. You know, you have to kind of consider where those are. There's space requirements. There's the distribution systems, the installation controls, and CX. So I give you the cheat sheet on what we're going to talk about. So the first piece are the utility impacts, and Brian mentioned some of the decisions that were made for his project, and you know, a couple of key points here. You know, what we've seen for costs of gas connections to the buildings can range from 20 to 45,000, and so that's the price to get the gas from the street to the boiler. And so those costs have to be factored in when you're doing comparisons. The other piece that has to be factored in are the venting costs. In California, a lot of the plants are on the roof, so the venting is pretty minimal. We do a lot of plants in the garage when we used to do a lot of gas, and those vents are a lot more involved and complicated to get out of these multi-use buildings. So that'd be kind of the first thing. There's a big savings there. The other part is on your transformer size. I've heard a lot of folks talk about how, this going to heat pumps is this huge transformer bump, and I have not seen that. If you're right sizing these things, the most I've ever seen is that you bump up kind of in one class, but I haven't seen a tremendous bump. Typical buildings, 1500 kVA might jump up to 2000. But again, you do have to kind of plan around that. You want to plan for both your peak heat pump as well as your peak backup resistance, however strategy you use there. Next piece would be the heat plant sizing. So Ecotope, along with Southern Cal Edison and SMUD, developed an EcoSizer program, and this is a program, I've got the website kind of shown down at the bottom, but this is a program that's designed specifically to size central heat pump water heating systems. What you'll need are a number of units, number of occupants, and some information about what type of plant you're planning your system around. And this system can kind of do some hot water simulation. It can do your sizing. It's got some variability, so you can kind of tweak, but it's designed around the designer. We have 25 engineers in house, and so we put it to the test and sort of made it this kind of iterative thing. So it's fun, and it's a quick way to kind of get to an answer. But this will also allow you to model a load shift pretty easily, so you can see the impact. The impact with load shift is that you need more storage. If you look in the middle of this graph, we've got a hot water simulation. The green line sort of shows the useful storage volume. And then the red line in this simulation will show when the heat pumps run, and then the blue is the draw of the building. So this is a one-day profile. In this particular building, we see a morning draw, and then we see an afternoon draw. We've got this shaded out area, that's our load shift. So if you look at the red, that's when we're not running. And so this shaded out area would be the part that we want to load shift, and this would be the peak rates inside utilities. And then we can also in this program model the swing tank. So you can see the swing tank never drops below 120, if you can see that. But this is sort of a tool to help validate your sizing and sort of understand how your system's going to run. In terms of the manufacturers that are available for central heat pump water heating equipment, again, Ecotope is supporting a lot of these products and these manufacturers, trying to get them to market and kind of find their spot. These are, I would say, probably the 5 leading contenders for heat pump water heaters to consider. Mitsubishi's got a new model coming out. Sandin, which is now called Senko 2 multifamily, they've got a new product coming out with their Gen 4 air source. Both of those first two are CO2 single pass devices. We've had quite a bit of success with the Senko 2, and we've got 2 pilots going in now for the Mitsubishi product. Both of those are really promising. Colmac and Nile are sort of the 134A and 410A. These are the HFC based cycles. Both of those are using refrigerant that are due to be phased out. The industry is already sort of lining up, like I had mentioned before, 513A will likely replace 134A, and then 410A will probably go to R32. And then there's some other options for that too, but those would be kind of the intermediate replacement refrigerants. So Colmac has a CXA and a CXV. Both of those can do are both air source devices, and they have kind of an outdoor temperature range they operate on. And then Nile and A.O. Smith have similar products, both air source 134A and single or multipass. And then the kind of the fourth class would be kind of your typical space heating 410A heat pumps that we put heat exchangers on and do low temperature DHW. I've done 3 or 4 systems like that, and you have to be really careful because there's not a lot of upper temperature range with those devices. So you don't have much in the way of storage. Next kind of consideration would be where you're going to decide to put your plants. I see a lot of domestic hot water plants in California on the roof. We've done them, rooftop. We've got a kind of a skid product we're working with Sandin on, or Senko 2 to develop. These would be, the idea would be plug and play devices. These would just get craned up to the roof and plugged in. We've also done ground mount, so just on the outside of a building with an adjacent mechanical room, and then we've done in the garage. So over in the left, you can kind of see we've got a big space down in a parking garage. This is a 360 unit plant here, lots of storage and some big Colmac CXA heat pumps.
Hey, Sean.
Yep.
On this topic of placement, have you ever run into any issues, for example, where you have, if you're using a split system and you have the condenser outside, have you ever run into any aesthetic concerns with the property manager or?
Absolutely. Yeah, no, we do. A lot of times we will screen projects if we're working on. The one on the upper right was a retrofit. We offered a kind of a screening fence and they were like, yeah, don't bother. So they didn't mind so much. A lot of the newer construction projects do mind. I mean, heat plants, boiler, the heat pump water heaters on the roof. Sometimes, I mean, we've run into design review boards saying that we don't want to see anything from the roof. So we've been really pushed down height-wise to make those less visible. We're actually entertaining with our rooftop skid shown putting the actual kind of siding louvered material right directly on the tanks so that they match. They'll sort of blend in with the facade color and shape. But we have run into concerns, then obviously, for rooftop and then the ground mount, and then obviously in the basement, those are tucked away in a room. And it's not super clear in the photo, but we're actually discharging the spent air out of the heat pumps through a louver back into the garage. So there's a lot of air movement in that lower plant in the garage. And I'll show some more details on that. But those are kind of your three basic mounting configurations. Here's some Revit layouts of our heat plant in the parking garage. So this is a big building. This is a 525 unit apartment. We can see we've got all of our storage on the upper level. And this is down in a below grade parking garage. And we've got our heat pumps on the level 2. So this is 2 stories below grade. What we've found putting heat pumps in the garage, we get about a half a COP increase in performance with the 134A devices. These are the Colmac heat pumps. And one thing I would say is that we typically will set these up in a room, duct the discharge air out, and then pull makeup in through a louver into that mechanical room. And then these are just using the buffered space in a below grade parking garage. We've never seen the parking garages get below 40, which happens to be about the end of most 134A equipment. Some of the equipment can operate lower than 40-degree entering air, but that sort of works out okay on these plants. We've got monitoring on several plants in Seattle in this configuration, and with Colmax, we're getting COPs of about 2.7 on the annual. Next important piece is the hot water distribution. So the distribution systems now, those are 24/7 loads, and you get one shot to sort of insulate and do these. And there's a lot of strategies right now on how to reduce the losses. But at the end of the day, it really comes down to your piping surface area and the insulation value around it. This is commonly referred to as the UA, so the U value times that surface area. And the UA of your piping system is really representative of your heat loss that you will encounter. And there's a bunch of strategies to sort of get around or to try to reduce this. One would be to locate your plants kind of more central. So versus at the end of a building, you want to be located more central because you can take your hot water pipe and go straight up. If you look at this schematic on the left, and then split it left and right. And so what that does is it reduces the size of your pipe down there. And then this is a typical, as Gary Klein calls it, the rib cage design. We've got your spine down at the bottom, you've got your ribs coming up, and then we grab everything at the top and bring it down back to the DHW plant. Over to the right, this is an idea we've been doing in Seattle, which is shared stacks. The idea is you come up, and instead of feeding one stack per stack of apartments, you go in between two and you feed back to back. So what it does is you come up on this riser and you split it at each floor, right and left, right, left. So you got one riser now for 2 units. And so that, the riser gets a little bit bigger, but the heat loss goes way down. And so that's a really easy way to drive your losses down. This requires a bit of coordination with the architecture because your run out or your wait times are kind of the key. So you've got to make sure you get those lines located in the right place where feeding them from both sides doesn't present a prolonged wait. There's another strategy to reducing the UA, and that's to kind of right size. So hot water piping design has been sort of under the microscope for a while. We've had theories, we've had technologies and sizing tools that are based on really old data. So both with sizing of the central plants, which is what the EcoSizer does, and then IAPMO has released the water demand calculator. This is a great tool to help design right size plumbing. Most of our hot water and cold water plumbing for our buildings designed around Hunter's curve are significantly oversized. We see flows that are probably 1/5 to 1/10 sometimes of what we're designing for. So you can get away with a lot smaller piping design if you are allowed to use these. California hasn't quite adopted the Appendix M. Appendix M is really the alternate sizing approach, which allows you to do kind of right sizing plumbing design. And then the WDC is the actual tool that helps you design the pipe for the probability of flow. So this was based on a bunch of metered data, but based on what we've found, this calculator is almost is right on based on the data we've looked at in terms of predicting what the flow would be. So this is another area that'll see a lot more attention and focus, I think, as Title 24 starts to really hone in on some of this stuff.
Hey, Sean, just want to do
Yep.
a time check. We have about 3 minutes for your section.
Oh, okay.
And then we'll move on to Q&A.
All right, I'm going to cruise then. The other part is the hot water system insulation. So again, Title 24 has the requirements based on temperature and insulation thickness. Insulation and how you mount is really critical. So just making sure you've got fully insulated mounts. You can see one of our heat pump designs. We've got the mounts, the hard ceramics tied up against the structure there. So that's really crucial. The controls pieces are super important when you're setting these systems up. You do have to make sure you're looking at the ACM2 around the hot water controls. You do need a basic control, a monitor, and alarm system. The problem now is most of these systems, there's no way to understand remotely what's happening. And so it's really crucial that you understand when there's a problem that you get an alarm or a text so you can go work on it. So this is really crucial. I'd also add load shift and M&V, consider those devices for your control system. M&V is super crucial for troubleshooting. This is how we learned a lot about these systems, monitoring them. Commissioning, can't overstate this. Commissioning is super important. If we do a job and don't commission it, which we don't do, we always have problems. And what we try to do when we commission our jobs, our commissioning engineers will try to basically make every stage and every piece of the system fail and see what the backup is. And so we've got processes in play to kind of work on that. And then out of that work resolves a commissioning log, and that's an important tool for looking at or for kind of fixing things in the field. And this will help to bring all the contractors up to speed as well. There was a question about operating cost comparison. This is a project I'm working on in PG&E territory, and I looked at roughly when our heat pumps would run. I looked at the rates, at the time of use rates, and over to the right is kind of my summary. This was a project that had 4 individual buildings. They were sent with central gas. They were running the piping underground between the buildings, so huge losses there. Building by building gas. And then if we did central heat pumps, we can kind of see the annual costs. And then if we did it with load shift, there's a little bit of reduction there. This is a low income project, so the time of use pricing isn't as aggressive as the as kind of market rate. And what we're hearing is that time of use pricing, I mean, that's a crucial piece. And with central heat pump water heaters, that peaking, really getting out of the peak is kind of the real motivation around doing central heat pump water heating. And I think I'm close. I've also got 2 quick case studies I could just run through if I have enough time, Myra.
Hey, Sean,
Yeah.
this presentation will be sent out to everyone that registered.
Okay.
So we could just have that as part of the takeaway for the
Okay.
attendees.
Okay. Well, there's my sneak away. There's the 2 shots of 2 different projects. This is a large one, and this is a smaller one with Sandins. Both of these systems are up and running right now. Yeah, and that's what I've got. And I've got the EcoSizer up there on the last slide if you want to look at that. And that concludes.
Awesome. Thank you so much, Sean. It was a lot of good information, and I'm sure our attendees really appreciate it. So at this time, I'm going to kick it over to Blake, and he's gonna we're gonna go through some of the questions. We have gotten quite a bit of questions, and so if we don't get to your question during the next 10 minutes, we will respond and send out our responses to all the attendees. So I'm going to switch it over to you, Blake. Oh, Blake, are you there?
Yes, I'm here. I'm working to read the questions. It's a
Okay.
little bit of one question, what's the typical commissioning cost? I guess that would be versus gas system. So specifically, Sean, do you think it's a higher or the same commissioning cost?
It probably is a little bit higher, just because there's more involved. It's a I would say it's a more advanced system than kind of your basic gas approach. And one thing to keep in mind are most of the gas systems, I mean, they've had 100 years to kind of work on the controls and the optimization, and the heat pump world is kind of just coming online in terms of the systems. And so I think that, you should plan on a little bit more activity around the commissioning side, mostly to kind of test all your systems out.
That sounds good. Here's another one. Can you explain how the complexity of the system scales up with demand? It would be easiest to understand demand and complexity relative to unit count. So this is specifically asked by a developer who builds wood frame buildings in the San Francisco Bay Area from 100 to 350 units.
Yeah.
So from 100 to 350, how much more complex? I think is the question.
Yeah, that's a great point. I think that the elevation of the building, i.e., if it needs boosters, will really drive the price can drive the complexity up a bit. We have to do the temperature maintenance a little differently in true high rise. So these would be, 8 stories and above. So if we're talking about adding more units, a larger development, then the high rise stuff does really kind of change it. But if we're talking about comparing, say, a 100 unit and a 300 unit, I don't think, I think it's the same thing. And you can, the designer can choose whether to do this in multiple plants or to do it as one big central. Doing it as one big central will be cheaper. That's currently challenged right now in, I guess, the Title 24 stuff. I'm not exactly sure where it is or what folks have had experience with. I know others inside of my firm are much more familiar with that, but I would say that I think that the complexity, I don't think it sort of scales with the size of your apartment. I think that if a 100 unit and a 300 unit, it's going to be the same approach, and it's really just there's a size, there's a storage size, there's a heat pump size. Those would scale up, but I think in terms of the overall effort, once you've decided to go to heat pumps, whether it's a 100 or a 300 unit, it's just going to be a larger system. But I don't think it necessarily gets more complicated with size. I think once you've gone to the heat pump, then you decide what type of heat pump, what type of approach, and then it's kind of the same math, really.
Great. I'm going to ask another one that I know we went through when we were doing some practice, and I found really interesting, and then go into some questions for you, Eric. What is the incremental upcharge for the increased electric capacity required for electrification, switch gears, transformers, etc.?
Yeah, I don't have a good number on that, other than to say that on our 100 or 200 unit, we've had to bump, say, the transformer up by about one size up. So that might be the kind of the incremental, but it wasn't a huge sort of increment. It wasn't mind-blowing, shocking. I think one project we went from 1,000 or 1,000 to maybe 1,500, and that was that was about 130 unit apartment. So so I don't think that the increment the incremental utility and transformer costs from the building side, this I don't know what the utility side, how they treat this, but the building side, I don't think it's a huge increment to add the central heat pumps, and it hasn't been a huge increment, and especially the more central you go with these systems, the lower your kW draw is. I mean, that's something that we have found. And so, there are things that you can do as a designer developer. But I haven't seen a huge increment, and I also don't have those numbers. We did do some analysis on that, so I can find, I can dig up those numbers if you want to email me. Based on what we found for some of the prototype analysis.
That sounds
Eric,
great.
I want to see if Eric has any if he has any information on this topic.
So we actually separate because we use a centralized water heater. We had to have 2 transformers in that whole undergrounding of Smut's overhead lines. Both transformers were actually 208. 2,500 amp transformers, and I think when we were on the cusp of a 480, I think we were really turning a lot of those and kind of sharpening our pencils in terms of appliances and sort of what we're using in the building to really bring that down. But I think we were on the very brink of upsizing our transformer, but we were able to avoid that. So I think it done, but it also depends on the product type. We have mainly studios and 1-bedrooms.
All right.
Question for Eric. When you went through the $80,000 gas boiler equipment cost, did that include venting and the space that venting takes, or was that not included in the cost exercise?
No, that wasn't included in the cost exercise. We were really just kind of trying to compare equipment to equipment. Like Sean said, we didn't take well, we took into account bringing gas into the building, but that's just sort of an extra boost for our decision. But no, that 8,000 was just for the equipment.
Oh, gotcha. So it looks better if you include piping and venting.
Right.
Um,
Right.
and then a follow-up, this is somewhat regarding venting. What are the externalities associated with floor area limitations from your perspective, um, both on the heat pump side and the gas side? Do you feel like you lost any floor area going either way or gained anything back in terms of getting
Um,
vent risers?
no, I think so. We initially designed that boiler room, kind of the general layout for a gas boiler. So we kind of had to squeeze everything into the heat pump room, or to when we converted to heat pump. And I think the good thing about heat pumps is, especially depending on your footprint, you might be able to put the heat pumps on the roof, or in the garage, which is most likely what we're going to do. So I wouldn't say there's a huge difference in space. I think the biggest difference is that the transformers. I think that takes up probably the most space. If you, for example, if you upsize a transformer, you're going to need, that can almost double your space for the alcove, or 50% more.
Thank you. This is a question for probably more for Sean. Are there ground source heat pumps for domestic hot water? This is from Craig Stradley.
That's a great question. I have not seen, I mean, there are ground source heat pump technologies out there. They're really water to water heat pumps. Most of them are either 410A, and there's a few 134A devices. But I've used both of those for domestic hot water. I've used a 410A system for domestic, and I was able to make 120 just barely. That's a 410A device. So that's your traditional water to water ground source heat pump approach. I've also done wastewater source. And so this is an approach where you collect and gather all the wastewater and then suck the heat out and put it in basically tomorrow's hot water. So today's waste, tomorrow's hot, using water to water heat pumps. That's a pretty interesting technology. And as far as coupling a 134A to the ground, that's probably limited. The 134A cycle, starts to have problems around 40-degree entering water, and our ground loops tend to go lower than that. So I think that the 410A is probably the best option for ground source right now. I haven't seen any products that have tried to do it with other refrigerants. And yeah, I think that would be the case there.
Thanks,
Okay,
Sean.
we got one
Hey,
last one before we go to
perfect.
tech list here.
Thanks.
The question from Eric Hansen. Is it possible single pass would result in less storage space on a large project? I think wondering if it might be worth going to single pass just to save some space.
Yes, it can be. And the factor between the two, I think, is what we term storage efficiency. And if you look in ASHRAE, in a traditional kind of boiler hot water storage scenario, so about 60 to 65% storage efficiency is about what they claim, and that's a typical multi-pass setup, which is gas boiler. Heat pump would do the same. And then with single pass, your storage efficiency is probably closer to 80%. And when we say storage efficiency, it means if you have a 100-gallon tank, as you start to draw off of that, the cold water will come into the tank and mix it around, and then mixes it down so far that it's unusable. And so that original 100 becomes 60 gallons. And that's what storage efficiency is. And just by the nature of doing single pass, where you're not trying to mix it, but actually banking on stratification, you're going to need a lot less storage. So 60 to 80 is sort of the difference. And so when the projects get larger, it starts to make an impact on your footprint. So I would definitely encourage single pass for that reason, which is to save space, and then some of the other reasons as well, especially sort of the load shift, because I think that's going to be a really big deal in the future.
Great, thank you. I think we're into the live tech assist section. We have a project or two that came in and gave some information for Sean to give a little help with. I'll make you the presenter. I don't know if you've any screen to share there, Sean, or not.
Yeah, let me hold on a second. Let me grab the email.
And as Sean does that, I'll go ahead and unmute Madeline and Renner with, I hope I'm pronouncing this right, Mogovero Architects. So I'll go ahead and do that now. When I unmute you two, you will also have to unmute yourselves from the control panel. So Madeline, you are unmuted. You can go ahead and introduce yourself, and Renner, you're unmuted as well.
Thank you.
Can you hear me?
Yes.
Okay, great. So are we ready?
Yeah, please introduce yourselves, your project, and what your questions are in relation to all electric construction on your project.
Great. Well, thank you so much for having us. My name is Madeline Sagas, and I'm the project manager for Fort Visalia, Lofted Fort Visalia, which is all affordable multifamily housing project in the Visalia, Central Valley. And so we are considering all electric, which I will get into in a minute. The project is a 3-story elevator served building, which has also some walk-ups in the middle of it. And it's 80 units in 3 stories again. And it's a mix of 1 and 2 bedroom units. We have very little commercial space, which is really more for offices and common gallery space for the community. And we are at this juncture right now because we have been told that the client wants to pursue HSC as funding, and amongst other funding sources, and that's going to drive the need for an all-electric hot water system, whereas we're previously going the gas route, which is, we've learned more cost-effective upfront. So we just wanted to ask, this is not a high-rise building, this is only 2 stories. And one of the things about 3 stories, yeah. So 3-story, 80 units, it's about 80,000 square feet DSF. And what we wanted to know, we've come against some challenges in trying to make a decision about the project. Obviously, if we do get the HSC funding, well, that incentive, just like the SMUD that was discussed earlier, was going to push us to do it. So if we do all electric, we're looking at both the domestic hot water heaters in individual units, or we're going to do the centralized. So I just wanted to, so the option 1 would be central hot water systems. All the units will be electric, no natural gas, or central DHW heat pump systems. 1 DHW system per each of 4 zones, and that's because our building is a little bit spread out, and so we are, just as the diagram is showing, we would have 4 zones. And so we are looking at heat pumps, water heaters located in penthouses of roof, and storage tanks located on the ground floor. And that's because we have very limited space, both on the ground level and the roof level, where we have PVs as well. So we can't really fit everything in one place or the other. We have to split it. The storage tanks would be on the ground level. And this is a very expensive option, first cost, and ducted cold air discharge from the DHW heat pump is a concern. using its own recirculation loop, and the house electric meter will record the DHW energy costs. So that's one option we're looking. The other option is the mixed electric and natural gas. The alternative to the all electric site has plumbing considerations. All the units are all electric, no natural gas. Each apartment would have 50-gallon heat pump in an indoor closet, and the cold air discharge from the water heater closet into the space is a concern. There would be no recirculation loops, and each unit could have its own gas meter, but at a considerable cost. So those are the two all electric options we're looking at right now, and we're mostly concerned with the heat pump water heater situation that we are expecting some temperature drops below 40 degrees and in Visalia. And so unless we put them inside of the units, both having them on the roof or having them in the balcony, because we have very limited space inside of the units as well, would probably make could make this project, this option non-workable. So we would like to know what people have to say about that, and about the cost difference between these two systems. Obviously, for an affordable housing project, first cost is also really important, even though operating costs would be nice to be able to incorporate that. Yeah, and any other question, other comments that you may have about the system that we're considering right now.
Right. Yeah, this is a great introduction. I guess I can jump in here. First question I have is, can everyone see the screen that I've got up?
So we can see your screen, Sean.
Okay, great. So that was a really nice introduction on the project, and all of the things that you talk about are fairly typical of what we're seeing. So this is a great kind of example, and yeah, I'm happy to have this kind of discussion. I have reviewed kind of the basics of the building. I've looked at the proposed heat pump approach. As you mentioned, storage tanks in the ground floor on the slab and the heat pumps up top, which we can see in this drawing. It's a little hard to see, but we've got 4 plants as been laid out. So first, I think that is, in terms of a heat pump water heating system, I think that this approach is pretty good. I think that the heat pump that you've got is a 134A device. It's this one in particular is made by A.O. Smith. And I think that, based on what I showed, those will start to kind of fade out at around 40. So you will want to plan for some backup here, backup resistance. I would say that one thing to keep in mind is that the more central your system is, the lower the kW draw is. And that is pretty much universal. And so the option of putting the individual heat pump water heaters inside of each of the units and essentially going 1-to-1 will drive up your peak loads a lot higher than a central system. I also think it'll cost more to do individual heat pump water heaters per unit versus a central. I don't know how the costs for this proposed system have come in. I've seen some other costs in kind of what I would call immature markets in California. And so there's a big range out there. But I think that this general approach is key, and I think it's actually pretty indicative of what we find out there. Sometimes these central heat pump systems, the storage sizes can be pretty large, and so you really want to try to optimize around what your roof can hold. We've had to beef up some structure on a couple projects right along the corridor lines to get enough weight capacity to put the storage in. And so on bigger buildings, that's typically what we do. This being kind of a 3-story, this approach, putting the tanks down and your heat pumps up top, I think works pretty well.
Yeah, the weight of those storage tanks are, they're really, really, really heavy, and so we're concerned about the structural cost of doing that. But is there the downside of having them separated? Is there like a loss of efficiency that
You mean having the heat pumps on the roof and the storage tank in the garage?
yeah, on the ground level.
Yeah. There'll be a little bit of a loss there. I mean, it's just kind of typical with piping losses. But if you do a really good job on insulating that, it won't show up too much. I
Okay.
don't think it's that big of a, you want to really be careful when you take a pipe down through a building. You want to make sure you've got really good clamping systems so that you're not thermally on your way down.
So how do you deal with the when it drops below 40? You're saying that we would have to then go to resistance heating, and that is really inefficient.
Yeah. Yeah, because the heat pumps just kind of, they can't squeeze a whole lot more heat out of the air at 40. Some of the 134A manufacturers have some really sophisticated defrost cycles, Colmac being one of them, and so they can actually push their heat pump down. But remember, every time you have to melt ice, you're not running the heat pump, and so you're also at a loss of capacity as well as derate capacity. And with our 134A projects, we typically will engage an equal amount of resistance at the same size as our heat pump. And we'll just stage that in to replace the heat pump capacity. One thing to keep in mind is that when you go to central hot water, the loads go way down. And so it might not be as big of an ER load as you might imagine, but with 134A in climates that do get below 40 in locations, you can't really avoid it. You need to have that backup there because on the coldest day you won't be making heat.
Sean, this is Renner. I'm getting questions from my partner Craig as well on this subject. So he's noting that we're finding that a system with a daisy-chained multiple residential heat pumps is more cost effective.
Okay.
And we're curious about your response on that. Just we're finding that the resistance heat can actually become quite expensive on top of the system.
Okay. Yeah. I mean, it can. I mean, it can add load, right? Sorry, there was a couple questions there I'm trying to address. I think that the resistant, I mean, a resistance tank is typically what we use and a pump for our backup. Those systems tend to be about $5,000 when we're talking about a central loop. And so you're kind of replacing the heat pump capacity with a backup storage tank. That's an approach that we've used. You could also do it with sort of a tankless, but that's what we've been using. And then in terms of having the individual heat pump water heaters inside the units, it really kind of comes down to what you're seeing for install costs. Let's see, we did a job and priced out gas and central heat pump, and we found a $600 incremental cost in our markets with a contractor that's done 4 of these big loops. So $600 per unit was sort of what I would call a developed market price. Heat pump water heaters, individual in unit, those are about a $2,000, $2,500 install problem by the time you get done with the ducting, the condensate drain, etc. So that really becomes, I guess, the target for the central. And I would say that the central systems, we've seen come in above that 2,500 number, and I've seen them come in below, and especially the case of that larger one where we saw a $600 incremental. So I think a lot of this is sort of based on kind of where the market is. But if you think about it, a central loop should be a lot cheaper. And if you look at the actual cost of the equipment, it is way cheaper. And so the difference lies in the installation costs and that side of it. And what we see a lot are bids get padded to kind of manage the risk. And as this market sort of develops, as the manufacturers come online with more plug-and-play systems, which is what they're working on, we expect to see those costs go down.
Mm-hmm. And there's the maintenance part too.
Yeah, that's a really good point. The more central, obviously, the maintenance is way less. I mean, there's not a whole lot of maintenance in a lot of the commodity level products, but like the individual heat pump water heaters, kind of the integrated units, those are kind of designed to be put in the field and run till their death. But the more central systems, you do have to clean the coils. They do muck up. You're bringing air, depending on where what's there. So you do have to kind of clean the coils, clean the filters, and then you have to do refrigerant checks. You don't typically get into that at the smaller residential commodity level products.
Hey, Sean, Madeline and Renner, for the sake of time, I'll be wrapping up this presentation in the next minute. I do encourage the both of you to sign up for our actual tech assistance support. And Sean, if you could kick back the presentation to me, I'll go ahead and close this out. And those
Thank
last
you.
few slides, it'll have instructions on where to go to sign up for that. But just as a teaser, this is the type of support that we want to provide to all of the project teams. So yeah, thank you so much for participating.
Thank you so much, and yeah, thank you so much.
Now I just need to, oh, thank you for self-muting. One less thing I have to do. Okay, great. So let me just share my last few slides here. Oh, let me, this is my first time using this format. Okay, so now everyone should be able to see my screen. So as Eric alluded to, one of the things that really helped him make the decision to go all electric were incentives. So this is just a compiled list of the incentives that we know of so far. Eric participated in the Smart Homes program with SMUD. I also managed that program as well.
Myra, I think we don't see your screen. We just see the end of slideshow. Well, at least I do.
You can't see my screen. Do you see my screen now?
We do not. If you hit like escape, maybe it'll close the slideshow. Yeah.
Okay, I'm
Nothing
clicking
sharing.
on show my screen.
Yeah.
You can see my screen now?
We can. It's the slide sorter view.
Okay, can you see the presentation?
With the speaker notes screen, though.
With the speaker notes?
Display settings, duplicate.
Yeah.
How about now?
Still has the notes.
Okay, how about now?
Yay.
Okay, perfect. Thank you so much. So yeah, and this will be sent out to everyone that attended. So you'll have this information, and you can look up for your where your building is, which incentives are applicable, which programs are applicable. And just as a follow-up resource, this was our plug for the Tech Assistance Program. If you do want to sign up, go to allelectricdesign.org. And in addition to the sign up for Tech Assistance, there's also information on our other series, our contractor training series, and the remaining topics for our Roundtable series. If you are working on an all-electric project and you want to showcase it, PCE is offering all-electric awards. The submission deadline is December 11th, and you can apply on this website. And again, this will be sent out to everyone, so you don't have to write this down. So as I mentioned, this is part of a bigger series, our developer and designer roundtable series. We also have a contractor training So all of this information is on the allelectricdesign.org website, and we encourage you all to attend our next roundtable in Q1 of 2021 on non-res and high-rise multifamily HVAC. And with that said, I'll close out the presentation, and please fill out the survey that will be sent out immediately after this presentation. All right. Well, thank you, everybody. I will go ahead and close out. If you have any questions, please feel free to reach out to us.